Welcome back, everyone, to this continued discussion about the theory and intuition behind support vector machines. In this lecture, we're going to talk about hyperplanes and margins. We're going to slowly build up to the full support vector machine model, and that begins by understanding maximum margin classifiers. Then we'll expand those to support vector classifiers, and finally expand those to support vector machines through something known as the kernel trick. Let's begin by understanding a fundamental key term known as the hyperplane. Formally speaking, in an n-dimensional space, a hyperplane is a flat affine subspace of hyperplane dimension n-1. For example, in one dimension, a hyperplane is really just a single point. In 2 dimensions, the hyperplane is a line, and in 3 dimensions, the hyperplane is a flat plane. Keep in mind, though, typically when we're just discussing planes and hyperplanes, in 1 dimension, 2 dimensions, and 3 dimensions, we don't actually use the term hyperplane. We use the terms point, line, and plane. It's not until we really get to 4 dimensions and beyond that we use the terminology of hyperplanes. Now, in 1 dimension, as I talked about, a hyperplane is a single point. So if I have a single feature that is a 1-dimensional x, then somewhere along this line, a hyperplane could be thought of as a single point. In 2 dimensions, the hyperplane is a line. So we can see here the hyperplane is just a 1-dimensional line. We're taking the number of dimensions and just subtracting 1 from it, and that's what your hyperplane looks like. Which means, in 3 dimensions, the hyperplane is really just a 2D plane, or a flat plane. Now, the core idea behind support vector machines that we'll eventually realize is what we really want to do is use hyperplanes to create a separation between classes. Then new points will fall on one side of this separating hyperplane, which we can then use to assign a class. Let's start off with a very simple example. Imagine a dataset with 1 feature and 1 binary target label. So we can go back to that baby chicks example we talked about earlier, where we have a weight feature for baby chicks, and depending on how much they weigh, we classify the baby chick as male or female. What would this look like if we actually visualize this feature? Well, we would simply place the points that we already know the labels of along this feature. We can think of this as our training dataset, where we have a single 1-dimensional line representing weight, and we have some points classified as male and some points classified as female. You should notice in this case, the classes are perfectly separable. This is unlikely in real-world datasets, so later on we're going to learn how to deal with classes that are not perfectly separable. But just to understand the basics, we'll deal with this simple situation. The idea that we're eventually going to build up to with support vector machines is to create a separating hyperplane between the classes. And recall, when we're dealing with 1 dimension, the separating hyperplane is actually just a single point. Is there a point along this weight feature that I can choose to perfectly separate out the classes? A new point could then be classified based on what side of our hyperplane, or point, they land on. So if I have a new point here, it falls on one side of the hyperplane, so I would just label this as male. Similarly, if I had a point there, it falls on the other side of that point or hyperplane, and I would label it as female. That's really the main idea that we're talking about here. But the question arises is, how do we actually choose where to put this separating hyperplane? As I previously discussed, these classes are perfectly separable, which means there are many options that perfectly separate out these classes. You'll notice that if I choose any of these points, it would perfectly separate my training dots of male versus female. So I have to decide which of these points, or hyperplanes, is going to be the best separator between the classes. I need some sort of quantitative methodology to choose the quote-unquote best separator. And what we could do is use the separator that maximizes the margins between the classes. So here we can see that this separator kind of right in the middle is actually going to have the maximum margin between the hyperplane or point and the first instance of each class. And this is known as the maximal margin classifier. Keep in mind, this is not a support vector machine quite yet. We're still building up to it. Just like 𝒏𝒕𝒖𝒊𝒕𝒊𝒐𝒏 had to build up to support vector machines in his own research, as we previously discussed. So this is a very simple model, which is just a maximal margin classifier. choose the hyperplane, and then figure out the hyperplane that is going to maximize these margins and decide that that is then your best separating hyperplane. This same idea of maximum margins applies to n dimensions. Here we're showing it in the simplest case possible, where it's just a single point, and then your margins are the distance from that point to some other point along your weight feature. Now let's imagine this in a two-dimensional feature space, where we have something like the height and weight of the baby chicks, and then the two groupings of male versus female. Again, we're dealing with an instance of perfectly separable classes. So we know that a separating hyperplane in two dimensions is going to be a line. But again, there's multiple possible hyperplanes here. All of these lines actually separate out the classes perfectly, but there should be some ideal hyperplane. And if we're thinking about maximum margin classifiers, then we want to choose the hyperplane that maximizes these margins. And you should note that each data point here is actually a two-dimensional vector, consisting of information about the weight feature and the height feature. Since we can think of each point as a two-dimensional feature vector, I can begin to understand that the data points that are interacting with the margin are actually supporting the separator's decision to figure out what is the best separating hyperplane. Now, what happens if the classes are not perfectly separable? Here we can see 2 points for male and female, and then we can also see that there's not going to be any particular point that perfectly separates out these classes. So I can't figure out any hyperplane or any point along this single weight feature that is going to be able to separate without actually allowing for misclassifications. If I choose this particular hyperplane, you'll notice that I will misclassify the female point as male. If I choose this hyperplane here, I'm going to misclassify the male point as female. What we need to introduce is a bias variance trade-off, just as we've worked with in other models. And the bias variance trade-off depends on where we actually place this separator. Because wherever we place this separator, it's essentially creating ranges for what is going to be classified as male versus what will be classified as female. For example, here we chose a hyperplane that fit probably too much to the female training data. However, you should note that it's only misclassifying one single point. It's going to misclassify the female training point as male. But realistically speaking, we can see that there's probably too high of a variance fit to the training data, picking up too much noise from the female points. Because if we had a new test point, which is actually quite close to the existing female weights, it would still get classified as male by this particular hyperplane or point of separation. What we would like to do is use the bias variance trade-off to our advantage, because we can increase the bias by a little bit in order to substantially reduce the variance. And this is going to depend on where we actually place this separator. Notice that here, we're allowing for the introduction of more bias in order to reduce variance to lead to better long-term results on future data. We're still going to possibly misclassify points, but you'll notice this new point, as we introduce it, is going to be classified as female, which is probably much more in line with the training point weights for female. But this separator is still going to misclassify one male training point as female. So the distance between the threshold and the observations is a soft margin. Notice, now that we're actually allowing for the bias variance trade-off to perform misclassifications, there's going to be some points that are going to actually fall between the margin and the hyperplane, and this is known as a soft margin. Essentially, a soft margin allows for misclassification inside of the margins, allowing us to introduce more bias to our model in order to hopefully greatly reduce variance. Keep in mind that once we introduce the idea of soft margins, there actually is going to be many possible threshold splits. So how do we deal with this issue? Now that we're not actually dealing with a maximum margin classifier, we'll have to figure out what level of misclassifications should be allowed. In this case, we can use cross-validation to determine the optimal size of the margins, essentially testing out different levels of misclassifications allowed to be performed inside of the margins to figure out the best overall model. Let's take a look at this in 2 dimensions. For the 2-dimensional soft margin example shown here, these classes are actually still technically perfectly separable. If we went back and only used the maximum margin classifier, we would get a separating hyperplane that looked like this. Notice that we are technically not misclassifying any of the training data, but we're clearly picking up too much variance or too much noise from the female set if we're only allowing for a maximum margin classifier with no misclassifications. It's going to end up creating these zones where we're probably expanding the male classification zone too large. So instead, we want a support vector classifier, which allows for soft margins. That is the difference between the maximum margin classifier versus the support vector classifier. The support vector classifier is essentially adding in the idea of soft margins, or allowing for misclassifications to add more bias to our model. Notice that with the soft margins, we're allowing for the misclassification of this male training point. But we're able to get a better model that allows for the introduction of more bias to greatly reduce variance. Now we've only visualized cases where the classes are easily separated by the hyperplane in the original feature space. Allowing for some misclassifications still resulted in reasonable results. But here's the key question that moves us on from support vector classifiers to support vector machines. What would happen in a case where a hyperplane performs poorly even when we allow for many misclassifications? So for example, let's imagine some sort of general feature that actually resulted in a grouping that looks like this, where we have essentially a middle chunk as some label and then the outside as another label. Notice there is not a single hyperplane that won't separate out the classes without many misclassifications. So if I chose something straight in the middle or something all the way on the side, I'm still actually going to have a lot of misclassifications. Now you may be thinking, why not use multiple hyperplanes here? But that's going to be even more complicated when we start dealing with higher level dimensions. For example, take a look at this case. Clearly, there's no straight line that is going to be able to separate out this class. And there's not going to be a grouping of lines easily solved for that can fix this problem. Instead, this is where we have to go from a support vector classifier to a support vector machine. Support vector machines are going to solve the problem where your hyperplanes are not easily able to separate out your classes even when you have soft margins. So to solve these cases, we're going to move on from support vector classifiers to support vector machines. And the way we do this is through the use of kernels. Kernels allow us to project the data to a higher dimension or another feature space in order to use a hyperplane in this higher dimensional space to separate out the data. And we're going to talk a lot more in detail about this kernel trick and the movement to support vector machines in the next lecture. I'll see you there.